Lighting's kind of trash, but it's fine. I shouldn't record this late. The series, what is it? The series resistor plus capacitor lab. I'm gonna go over it, talk about some key ideas, and answer some of these questions on that page. So it's page 11 in your packet. Basically, what we have is like 3 resistors, right? And we have a battery hooked up to them, and we got a capacitor in essentially parallel, right? So it's kind of in parallel with one of the resistors. And what do you think is gonna happen if we like the instant we turn it on, right? What is gonna be the brightnesses of these? And we're gonna pretend they're bulbs because in the lab they're bulbs. So if these are light bulbs, what are gonna be the brightnesses of the light bulbs as soon as we turn on the battery? Hopefully you paused and thought about it. Really, the only 2 things that are gonna be shining the instant we turn on the battery are this bulb and this bulb, right? So I'll label them 1, 2, and 3 just while I'm explaining. It'll hopefully be easier that way. But only bulbs 1 and 3 are gonna light. Why? Because the current, right? The instant we turn on the battery, the current is gonna flow through bulb 3, and at this junction, right? At this parallel junction, it's gonna only go to the capacitor. When the capacitor isn't charged yet, it basically acts like a wire. A positive charge is going to end up on the plate of the capacitor, and then a positive is going to get pushed out of the other plate, completing the circuit, essentially acting like a zero resistance wire. So in that case, you're only going to have bulbs 1 and 3 alight, and in this circuit, it's only 10 and 3. Sorry, why did I say 10? I was thinking about the resistance. Only bulbs 1 and 3 are going to contribute to the total resistance, because the current is not even going to worry about the bulb 2 yet. So the total resistance is 20 ohms. If you do 9 over 20, here, let's do that really quickly. 9, so I'm doing the initial current. So the total voltage, right, of the voltage through this resistor, it's 0, right? No current is passing through. That's why it's not a light. So the voltage V initial of the circuit of the V initial of the resistor is 0 volts. If you want to find the current, it's just 9 divided by 20. I don't know how much that is, but 9 divided by 20 amps. I think that's 0.45 because I wrote down 0.45. But over time, what's going to happen is this capacitor is going to build up charge, and whatever positives are on this plate, they're going to kind of resist and push away from positives entering through that junction, right? As we're building its, what am I saying? As we're building the charge on that capacitor. So what's going to be so after a long time, after everything's settled, essentially T equals infinity. And if you take AP Physics C, you'll learn why it's not like, oh, after 10 seconds it's fully charged. It's really after a really long amount of time. It's because the charge, and that's a whole other thing I can talk about later. But after a long amount of time, T equals infinity seconds, whatever. Sometimes the textbook might say that. What's the current through this resistor? Well, now that it's fully charged, no more charge is gonna go through this capacitor. It's only gonna go through the resistor. It's like the opposite. Before it was only going through the capacitor, now it's only going through the resistor. So now we can use Ohm's law and be like, okay, 9 divided by 30 ohms, that's our equivalent resistance. We're in series. 9 divided by 30, I think it's 0.3, so 0.3 amps. What's the V final? Now the V final is going to be whatever the voltage consumed by the resistor is. So 0.3 times 10, that's 3 volts. Why? There's 2 ways to think about it. First of all, you can think about it with parallel rules. In a parallel branch, the voltage consumed by each path is the same. So this resistor and this capacitor in parallel, whatever the voltage is going across this resistor has to be the voltage of this capacitor by the parallel rules. A more sophisticated, not really correct, but another way to think about it is loop rule, right? I can use loop rule for any loop I want. I can even have a loop for this parallel branch. So my change in V equals 0. So the negative voltage by the capacitor, right? Because a capacitor reduces or consumes the voltage you can think of. Minus, well, we're going through the resistor backwards, so we're really adding I times R, which is really just the voltage of the resistor. And then, add to both sides, you get voltage of the resistor equals voltage of the capacitor. So that is kind of the key idea, right? Like that's a key concept to know, and that's going to help us with when you have, like, what if a capacitor is in parallel with two resistors? Now, the initial current, we only have this resistor, right? Because initially, as soon as I connect everything, capacitor acts as a zero resistance wire. All the current's going to go through there. And you're going to be left with current only going through the 10 ohm resistor. The equivalent resistance would be 10 ohms, so 9 divided by 10, 0.9 amps. And the V initial across the capacitor is 0, because remember, same voltage. So these two resistors have 0 volts used up, so this is going to have 0 volts. By our parallel rules, they better stay the same. What's the final current? Well, it's the same, right? It's literally the same as before, because after a long time, no more current's going to go through the capacitor. Just those three resistors, you get 0.3 amps. And the voltage consumed this time, right, by our parallel rules, whatever the voltage across here is, has to be the voltage across here. So equivalent resistor for these two specifically is 20. 20 times 0.3 is 6. So 6 volts across these two resistors. There's better be 6 volts across that, what do you call it? That thingamabob. The capacitor. Yeah, capacitor. So yeah, hopefully this makes sense. Test your understanding on the back page for where it says series problems. Try out page 10. I'm going to actually make a video on page 10. So try it out first before you watch it. Because, it's good to try things on your own first. Just try it out. All right, thank you for watching.